Hello my friends and welcome back to the Futech HD channel. The Cikopo-Palamonan Toll Road, Cipali Toll Road, is a vital infrastructure project in Indonesia, connecting Cikopo and Palamonan in West Java. At 116 kilometers, 72 miles, it is the longest toll road in Java, significantly reducing travel time compared to the traditional North Coastal Road of West Java. Opened on the 13th of June 2015, this toll road is a crucial part of the Trans-Java Toll Road network, aiming to boost economic growth and connectivity. One of the key construction techniques employed in this project is the precast concrete beam installation method, which has played a pivotal role in the construction of bridges along the toll road. The role of precast concrete beam installation. Efficiency and speed. The precast concrete beam installation method offers significant advantages in terms of construction speed and efficiency. Precast beams are manufactured in a controlled factory environment, ensuring consistent quality and reducing the impact of adverse weather conditions on the construction schedule. This method allowed the Cipali Toll Road project to progress rapidly, with the installation of precast beams being a streamlined process compared to traditional in-situ concrete pouring. In the case of the Cipali Toll Road, precast concrete beams were crucial for the construction of numerous bridges and overpasses. The ability to produce and install these beams efficiently contributed to the overall speed of the project, allowing the toll road to be completed within the projected timeline. Quality and durability. Precast concrete beams offer superior quality control compared to cast-in-place concrete. In a factory setting, it is easier to monitor and maintain the consistency of the concrete mix, curing conditions, and reinforcement placement. This results in beams with higher strength and durability, which are essential for the longevity of infrastructure projects like the Cipali Toll Road. For the Cipali Toll Road, the use of precast beams ensured that the bridges could withstand the heavy traffic loads and environmental conditions they would encounter. This focus on quality has helped in maintaining the structural integrity of the bridges, reducing the need for frequent maintenance and repairs. Cost effectiveness. While the initial cost of producing precast concrete beams may be higher than traditional methods, the long-term benefits often outweigh these costs. The reduced construction time translates to lower labor costs and less disruption to the surrounding areas. Additionally, the high durability and low maintenance requirements of precast beams contribute to significant savings over the lifespan of the infrastructure. The Cipali Toll Road project, estimated at Rp 12.562 trillion, $1.4 billion, benefited from the cost-effectiveness of precast concrete beam installation. By minimizing construction delays and maintenance needs, the project was able to stay within budget while delivering a high-quality infrastructure solution. Case studies in the Cipali Toll Road project. Section V. Kertajati to Sumberjaya. One of the critical sections of the Cipali Toll Road is the Kertajati to Sumberjaya stretch. In this section, PT Wijaya Karya Beton Tbk was responsible for the installation of PCI girder beams. These beams were manufactured at the company's facilities and transported to the construction site for installation. The use of PCI girder beams ensured the bridges in this section were built to high standards of quality and durability. Terminal 3 expansion at Soekarno-Hatta International Airport. While not directly part of the Cipali toll road, the Terminal 3 expansion project at Soekarno-Hatta International Airport serves as a notable example of precast concrete beam installation by PT Wika Beton Tbk. The project involved the erection of PCT girder beams, which were produced at the company's stockyard in the Surya Cipta industrial area in Karawang. These beams were then transported to the airport for installation, demonstrating the logistical efficiency and quality control achievable with precast concrete beams. Challenges and solutions. Land acquisition. One of the significant challenges faced during the construction of the Cipali toll road was land acquisition. By July 2012, 95% of the land required had been acquired, with the remaining acquisition completed later that year. The delay in land acquisition impacted the overall project timeline, but the use of precast concrete beams helped mitigate some of these delays by allowing other construction activities to proceed without waiting for the complete availability of the site. Funding and financial management. Securing funding for such a large-scale project was another challenge. The project, owned by a joint venture company PT Lintas Marga Sadaya, required substantial financial commitments. With 55% ownership by Plus Expressways Berhad and 45% by PT Bhaskara Utama, the project managed to secure a Rp 9 trillion bank loan commitment, which could only be withdrawn after full land acquisition. The efficiency of precast concrete beam installation played a role in convincing financiers of the project's feasibility and adherence to timelines. Addressing accidents and safety concerns. Since its inauguration, the Cipali toll road has seen a significant number of accidents, prompting concerns about safety. Transport expert Ophir Z. Tamim from Bandung Institute of Technology identified several factors contributing to these accidents, including design flaws, vehicle conditions, and driver behavior. Improving signage, road markers, and warning signs has been suggested to enhance safety. The use of precast concrete beams, with their inherent strength and reliability, contributes to the overall safety of the infrastructure, though continuous monitoring and improvements are necessary. Bali, a renowned tourist destination known for its stunning landscapes and rich cultural heritage, has taken a significant step forward in infrastructure development with the construction of the Bali Mandara toll road. This ambitious project, the first of its kind in Indonesia, stretches over 10 kilometers above the waters of Teluk Benoa. Connecting Nusa Dua, Ngurah Rai, and Benoa, this toll road aims to alleviate traffic congestion, enhance transportation efficiency, and support Bali's booming tourism industry. The need for a new transportation solution became evident as Bali prepared to host the 2013 APEC summit. With the existing bypass Ngurah Rai being the sole route connecting northern and southern Bali, traffic congestion was a growing problem, exacerbated by the increasing number of tourists visiting the island annually. The decision to build an elevated toll road over the sea was made to provide a swift and efficient alternative route, ensuring seamless travel across Bali's key areas. The Bali Mandara toll road project was spearheaded by PT Jasa Marga Persero Tbk, in collaboration with several other state-owned enterprises, including Pelindo 3, Angkasa Pura I, and PT Pengembangan Pariwisata Bali. A consortium was formed, comprising prominent contractors Wijaya Karya, Adi Karya, and Hutama Karya, to undertake the construction. The project, which began in March 2012, required a budget of 2.5 trillion Indonesian rupiahs, with 70% financed through loans from a syndicate of 6 banks. The construction was divided into 4 packages to expedite the work. This division allowed simultaneous progress across different segments of the toll road, ensuring the project stayed on track to meet the 18-month completion deadline. The contractors adopted a design-build approach, which involved integrating design, construction, and supervision tasks, thus streamlining the workflow and maintaining quality control. Land acquisition and preliminary works. One of the initial challenges was acquiring the land for the roundabout, which required careful planning to avoid disrupting local religious sites. Respecting local customs and beliefs, the roundabout's design was adjusted to ensure it did not infringe upon sacred grounds. Piling and foundation work. The foundation work involved extensive piling, with 12-meter-long concrete piles driven into the seabed at designated coordinates. The depth of the piling varied, with some areas requiring up to 4 piles for stability. Each pile was welded and protected with high-density polyethylene (HDPE) coatings to prevent corrosion from seawater. The piles were then cut to the required elevation, a task that involved precision and labor-intensive effort. Installation of pile caps and girders. Following the piling, pile caps were installed to support the road's superstructure. These caps served as bases for the girders, which were crucial in distributing the load evenly across the foundation. The girders, each 30 meters long and weighing 100 tons, were transported by pontoons and carefully positioned using cranes with a capacity of 150 tons each. This phase required meticulous coordination and handling to ensure the girders were placed accurately and safely. Construction of deck slabs and road surface. The deck slabs, which formed the road's surface, were either precast or cast in situ, depending on the location. Precast slabs were transported to the site and assembled, while in situ slabs were cast directly on the pile caps. The slabs were then connected and reinforced through additional concrete pouring, enhancing the structural integrity. Asphalt paving followed, utilizing over 50,000 tons of asphalt sourced from Surabaya to provide a smooth and durable road surface. Installation of barriers and road furniture. Safety barriers and road furniture, including signage and lighting, were installed concurrently with the paving. The road design also included special lanes for motorcycles, electronic toll payment systems, and surveillance cameras to monitor traffic conditions. Wind speed monitors were also installed to ensure the road could be closed during adverse weather conditions, safeguarding motorists. Environmental considerations. Given the project's location above water, significant attention was paid to environmental impact. Temporary embankments were created using limestone, protected with plastic sheeting to prevent contamination. Mangrove replanting initiatives were undertaken to offset any environmental disruption, with over 16,000 mangrove trees planted. Regular water quality monitoring ensured that the marine ecosystem remained unharmed throughout the construction process. Challenges and solutions. The project faced numerous challenges, including weather-related delays and logistical issues. The fluctuating tides and shallow waters complicated material transportation, necessitating careful planning and timing. Contractors relied heavily on tidal forecasts from the Meteorology, Climatology, and Geophysical Agency, BMKG, to schedule their activities. Additionally, construction had to be temporarily halted during extreme weather events, such as the Rusty cyclone, which brought strong winds and high waves to the region. Cultural integration. Respecting Bali's rich cultural heritage, the toll road's design incorporated traditional Balinese architectural elements. The toll plaza was designed in collaboration with the Bali Architects Association to reflect local aesthetics, blending modern infrastructure with cultural heritage. This approach ensured that the toll road not only served its functional purpose but also harmonized with Bali's cultural landscape. Project completion and impact. The Bali Mandara toll road was completed on time and officially inaugurated by President Susilo Bambang Yudhoyono in September 2013. The road has since played a vital role in reducing traffic congestion, improving travel times, and supporting Bali's tourism sector. It has facilitated smoother transportation for both residents and tourists, contributing to the island's economic growth and enhancing its appeal as a world-class tourist destination. Villamine Group was awarded the prestigious terminal construction project for APM Terminals in the port of Tangier, Morocco. Within 2 years, they transformed a 60-hectare area into one of the world's most technologically advanced platforms. The project involved constructing a vast and complicated network of over 1,000 kilometers of underground mains, service lines, cables, and wires. These were meticulously integrated with the massive concrete foundations needed for the largest ship-to-shore and container handling equipment available. The site was specifically designed to accommodate 3 main types of equipment ordered and installed by APMT. 12 ship-to-shore cranes were installed on the quay to load and unload containers, while shuttle carriers transported containers between the quay and the container stacking areas. Automated rail-mounted gantry cranes, ARMGs, were installed in the stacking areas to pick up containers from the shuttle carriers and stack them up to 5 levels high. Control and monitoring functions were centralized in the administrative building, with monitoring facilitated through a vast underground double network of electric and fiber optic cables, meticulously woven around the main underground structures such as foundations, piles, sewer pipes, and water lines. The construction required significant groundwork, including the importation of 1 million tons of granular material and crushed rocks delivered by self-discharging vessels from Norway and Scotland. The container stacking cranes were mounted on 14-kilometer rails, necessitating solid concrete foundation beams. To meet the project's tight deadlines, Villamine imported 4 units of 20-meter customized steel formwork for precise 80-meter daily pouring production, using 70 tons of reinforced concrete for these foundations. To ensure perfect leveling of the foundation beams for the stacking cranes, Villamine and its partners designed a patented custom-built, laser-guided concrete grinder and core drilling melon. This innovative method allowed rails to be mounted straight on the prepared concrete beams without traditional, time-consuming leveling methods. After welding the individual units into one continuous rail, they were bolted to the foundation beams and checked for verticality and parallelism. The key area needed to support 12 Super Post Panamax rail-mounted ship-to-shore cranes, each weighing about 3,000 tons. The landside trailer beam was connected to and mounted on a row of 414 reinforced concrete foundation piles, each with a diameter of 1.35 meters and a length of 26 meters. Drilling rigs operated 24/7 to drill and excavate boreholes up to 7.5 meters into the underground bedrock. Every delivery from the batching plants was checked for consistency, and an independent control agency with an on-site laboratory controlled the quality of all processed concrete. Simultaneously, foundations for the workshop building, which included 2 floors of office space and a large workshop area for maintaining the shuttle carriers and other equipment, were started. Several layers of solid cement-treated base, finished with asphalt or pavement, were superimposed to achieve a combined thickness of 50 or 80 centimeters, depending on the traffic load intensity. The container stacking areas were finished with a double asphalt layer designed to withstand the load of containers stacked 5 levels high. Other areas were finished with concrete pavement blocks to endure the heavy dynamic traffic loads. At the quayside, the ship-to-shore crane rail beam was connected to the top of the drilled foundation piles. This beam, 1,200 meters long with a 2 by 2 meter section, was poured at a rate of 20 linear meters every 2 days. The last row of each of the 3 container stacking sections was designed for refrigerated container storage. Power for the cooling units was supplied from 3 dedicated reefer substations and distributed to feeder pillars at each of the 51 reefer rack constructions. On Section 1, the first high-technology container stacking cranes were mounted on the top of the installed rail. Terminal construction activities were meticulously planned to guarantee the acceptance and installation of different equipment batches by APMT. The project was divided into over 40 intermediate milestones for step-by-step handover to APMT. In February 2018, the first shipment of ship-to-shore cranes arrived from China. Except for the container stacking areas, the entire terminal was finished with concrete pavement blocks, requiring about 20 million blocks. Several teams worked around the clock to ensure optimal productivity. All construction activities were overseen and controlled by highly qualified surveyors. The project advanced significantly, with large areas handed over to APMT. The workshop building was also completed. Shuttle carriers transported containers between the quay area and the stacking zones. To ensure precise orientation of these shuttles, a grid of 730,000 magnets was installed in the concrete pavement blocks. Willemijn deployed a survey rowboat for fast and precise drilling indications for these magnets. Willemijn Group also handled all electrical works. An extensive double fiber optic network was installed to connect the control rooms to each individual equipment item on the terminal. All cranes, cameras, gates, power stations, and auxiliary installations were monitored through this network. To guide traffic within the operational terminal, over 30 kilometers of markings were painted on the pavement. A total of 9 substations were constructed. 1 main intake substation for the external power supply, 3 key substations for the cranes and other installations in the container yard, and to guarantee water supply in case of emergency, a water tank and 5 water pumping stations were installed. 2 of these stations were equipped with both electric and backup diesel pumps to ensure sufficient flow and pressure to feed the 90 hydrants across the site. A team of 60 motivated engineers and administrative staff coordinated over 600 workers on this project, preparing and controlling strict and safe working methods according to the project schedule. The APMT terminal was opened less than 2 years after construction activities began. Willemijn Group is proud to have delivered this world-class project to APMT within the projected timeframe and budget. A combined effort of 3 million man-hours was dedicated to this multidisciplinary project without any serious injuries. The terminal has an annual capacity of 5 million tons and serves as a transshipment hub for Maersk Line and its partners, conveniently located at the Strait of Gibraltar, where 60,000 cargo vessels pass through each year. The construction of the Quay Wall at the new Tema port facility, using caissons cast on land, showcases a meticulous engineering process designed to create a robust and enduring maritime infrastructure. This method, involving the use of massive concrete structures, demonstrates innovative techniques to ensure stability and functionality in challenging marine environments. Located in the seabed 19 meters deep, the construction begins with the dredging of a trench specifically designed to accommodate 74 individual caissons. These caissons, crucial components of the quay wall, are not built at sea but rather cast on land. Each caisson unit is an impressive feat of engineering, requiring 1,000 cubic meters of concrete for its construction. This ensures each unit is both structurally sound and capable of withstanding the harsh conditions of the marine environment. Transporting these colossal structures from the casting site to their final position at sea is a carefully orchestrated process. After completion, the caissons, each weighing a staggering 2,600 tons, are maneuvered onto a floating dock. This delicate operation utilizes inflatable airbags, allowing the caissons to be rolled onto the dock without compromising their integrity. Once securely positioned on the floating dock, they are transported to the designated location near the quay wall. The next phase involves strategically sinking the floating dock, a process that submerges the caissons into the water. This deliberate sinking maneuver is facilitated by tugs that carefully navigate each caisson into its precise position along the seabed trench. To ensure stability and anchorage, the caissons are then deliberately filled with water, effectively securing them in place. With the caissons now securely positioned, the final stages of construction commence. Each caisson is filled with sand to further anchor it to the seabed. Upon this foundation, the deck of the quay wall is cast, creating a solid and functional surface for port operations. This integrated approach ensures that the quay wall not only meets structural requirements but also provides a stable platform for the loading and unloading of cargo, essential for the efficient functioning of the port facility.